my name is Helen Dacre. I'm Associate Professor of Meteorology at the University of Reading. And thank you very much for the opportunity to present the work that we've been doing designing a proof of concept tool to support aviation stakeholders during volcanic ash events. This work has been performed at the University of Reading in collaboration with Rolls-Royce, who are engine manufacturers, and British Airways, who are obviously airline operators, and also the Civil Aviation Authority, who are the UK airspace regulators. So I'm aware that most people in this room are not physical scientists, so I'm going to spend some time outlining the problem that we're trying to address. So as you can see on the image on the left-hand side, Iceland contains over 30 volcanic systems, and typically they erupt once every 4 years. Now, usually the disruption caused from an eruption is fairly minor because the eruptions are of short duration and the volcanic ash is transported towards the northwest by the prevailing wind, so not into the really busy European airspace. The animation on the right, which is quite mesmerising, I can see all your eyes are getting a bit funny, is provided by the National Air Traffic Services, and it depicts a typical day, 24-hour period over UK airspace. So European airspace is the busiest airspace in the world. So occasionally, volcanic ash can get transported towards Europe, and that's when we experience really major disruption. So for example, back in 2010, you'll remember the Eyjafjallajökull volcano in Iceland erupted for a period of about 4 weeks, so it's a long duration eruption. And European airspace was closed for approximately 6 days at the start of that eruption. So that caused the cancellation of over 95,000 flights, affected more than 10 million passengers, maybe you were one of them, I'm not sure, and it accounted for about 48% of global air traffic, and that's because European airspace is so dense. It also had quite large economic consequences. The aviation industry were losing about £1.2 million a day, and over the entire eruption, it's estimated that they lost about £1.1 billion. So there's several decisions that need to be made during a volcanic eruption, both in terms of safety and also in terms of economic decisions. There were some positive outcomes of the 2010 eruption, the main one being that the communication between the meteorologists and the volcanologists and the aviation industry improved very rapidly in a short space of time, and that communication has continued over the following 8 years. So who are the decision makers during a volcanic eruption? Well, the responsibility for deciding where and when to fly when there is potentially volcanic ash in the atmosphere lies with the individual airline operators. However, having said that, their decisions rely on quite a number of other people. Firstly, they rely on the engine manufacturers, and this is because individual airlines don't own their own engines. They lease their engines from the engine manufacturers, and the engine manufacturers have a requirement to certify their engines to certain tolerances, so they perform tests to decide what the susceptibility of their engines are to volcanic ash. The decisions made by the airline operators are also made in conjunction with the regulators, the airspace regulators, and that's because any decisions they make have to be in compliance with the safety risk assessments that they produce, which are approved by the Civil Aviation Authority. And then finally, a lot of the information which the airline operators are using to make their decisions comes from the volcanic ash advisory centres. So they provide advice on the evolution of ash as it's moved around in the atmosphere. Some of those volcanic ash advisory centres provide quantitative, concentration-based forecasts, but many of them don't. And that's because there is very large uncertainties associated with the volcano characteristics, with the meteorology, errors in the wind fields, and also in the representation of some of the physical processes which affect volcanic ash in the atmosphere as it travels, like sedimentation and deposition. So back in 2015, we started well, we started in 2010, but in 2015 we held a workshop with many of the aviation stakeholders, and the purpose of this workshop was to determine whether they inferred uncertainty in the deterministic forecasts which were provided, whether different kinds of graphical information made them make different decisions. And during the workshop they were given a survey, and one of the questions in the survey was if you were presented with this hypothetical volcanic ash concentration map, as you can see here, and you're told that it's not safe to fly in the red area, then what would be your no-fly zone? Can you draw your no-fly zone? And this is the result. So this is a heat map of the no-fly zones drawn by those aviation stakeholders. So what you can see is most people infer some uncertainty in that red area. So most people drew an area which was larger than the red zone, and the mean was over 300% larger, so there's quite large uncertainty. But there's also a big range. So a couple of people drew areas which were smaller, and a couple of people drew areas which were over 1,000 times larger. So our conclusion from this really was that people are inferring uncertainties in these deterministic forecasts, but the level of the uncertainty depends very much on their own experience, their personal experience, and their own risk appetite. So typically those in operations drew smaller areas, for example, than those in research, who may have some appreciation of how these models work and some of the uncertainties there. In the discussions following the survey, it became very clear that although the operators and the decision makers were inferring uncertainty, they did not want uncertainty information. They wanted deterministic forecasts. They wanted what they were already getting. And the reasoning behind that appeared to be that they felt that any uncertainty information would complicate things and result in information overload. So would they be able to make fast decisions, which they need to in an operational setting, about where to fly and when to fly if they're given, say, probabilities about the concentrations of ash? So we've been working very closely with Rolls-Royce and the Civil Aviation Authority and British Airways to try and address this challenge, to try and design a decision support tool which is both fast and robust so that it can support decision makers during volcanic ash events. So by robust, I mean that it includes some quantitative appreciation of the uncertainty in the data used. So basically uncertainty in these models, which a lot of the decision makers are basing their decisions on. And by fast, I mean that we can condense the information so that we don't result in information overload for the decision makers. And the way that we approach that is by displaying the information in the decision space of the individual decision makers. So we designed an experiment to try and move from uncertainty towards risk, to try and quantify the uncertainty. So what we're doing here is we are imagining a hypothetical eruption of Katla, which is one of the volcanoes in Iceland, and we're using the London Volcanic Ash Advisory Centre dispersion model to make a prediction, a forecast of where the ash which is released from the volcano is going to travel in the atmosphere over the following 3 days. So on the right-hand side here, we just have some snapshots of where that ash goes. And I know you're not meteorologists, so basically what we have here is a big region of high pressure in the North Atlantic, and the ash travels clockwise around that region of high pressure. So eventually it's spread all over the North Atlantic. So it's going to be a big problem for any flights which are going from the States to Europe. Now, as Lenny and many others yesterday pointed out, our models are just our best. They contain our best understanding of the physics of the atmosphere, but they are inherently wrong. And they're wrong for a variety of reasons. Firstly, in terms of the wind fields, the atmosphere is chaotic, and so it's very difficult to predict very precisely where this ash cloud is going to go. You can just get a feel from these snapshots about the complexity of the movement of the ash. Maybe a larger source of uncertainty is associated with the volcano characteristics. when did it start erupting, how much ash was coming out of the volcano, what size were the particles. So what we've tried to do is we've tried to, instead of using a single deterministic forecast, produce an ensemble of forecasts. So the method that we use to produce this ensemble is as follows. First of all, we carried out quite extensive expert elicitation to look at both the input parameters and the internal model parameters which are used in the model. And we used our experts to determine the ranges of plausible parameters. If we are observing the ash, for example, to get to 8 kilometres up in the atmosphere, what's the uncertainty on that? Is it plus or minus 100 metres, or is it plus or minus 2 kilometres? So what are the plausible ranges? And then we perform some statistical emulation, which allows us to run lots and lots of scenarios where we vary each of these parameters. And the idea of this is that we can identify which of those parameters that we're perturbing is the dominant, or are the dominant parameters. So we can kind of reduce this parameter set down a little bit by using this emulation technique. You don't need to understand the details of that. If you're interested, then it's published earlier this year in an NHES paper, Harvey et al. Following this emulation step, we have used the most dominant parameters and perturbed them for our hypothetical Katla eruption. And this has resulted in a 600 member ensemble. So basically, instead of having a single forecast, we now have 600 forecasts where we perturb the parameters which are controlling the uncertainty. Now, once we have an ensemble, then we can start asking questions about the probability of encountering ash over certain thresholds. So we can say, what is the likelihood of encountering ash with concentrations more than 4 milligrams per meter cube, for example? And we've displayed this in terms of model agreement. So how many of those ensemble members, what proportion of those ensemble members are predicting ash over a certain concentration threshold? So on the top, we've got a map of the likelihood of the concentrations being above the threshold. And on the bottom, we've got a vertical cross-section along that flight route shown on the map there. So from JFK to London Heathrow and back again. And what you can see on the bottom is the scale that we've used, which we came up with in conjunction with our aviation stakeholders, which describes using probabilistic terms, whether the chance of encountering it is very likely, likely, or less likely. So you can see in some parts of this map, we are very likely to exceed concentration threshold, and in other parts of the map, we are less likely. And the black contour on there just shows our control simulation. So that's our best estimate, for example, of the volcano and the meteorology. And you can see that many of the ensemble members are predicting that we're going to exceed concentrations outside of that control, which just shows the range of uncertainty. Another thing which is quite interesting from here is you can see that the uncertainty, the spread around the control is not symmetric. So it's actually, in some places, we're really confident. Well, a lot of the ensemble members agree on the level of ash, and in other places we're less confident. And if you think back to that heat map, everyone pretty much drew a symmetric chart. So we're overestimating the uncertainty in some places and underestimating the uncertainty in others. Now, the problem with this is that if you want to make a decision about whether to fly this route, if you're working for an airline, then actually the number of charts starts to multiply, because you need different charts for different concentration thresholds, and you're also going to look at different lead times, so different forecast times ahead. So you might end up with 25, even 50 charts for a flight. And then we come into this problem that the airlines were worried about, which was information overload. If you're presented with a big pile of charts and you have to make a decision quickly, how can you actually assimilate all that information? So how can we condense the information to maintain the robustness of the decision, but also try and help to make faster decisions? So the way that we have approached this, and it was mentioned briefly yesterday, was to use a risk matrix. So if you're not familiar with this, a risk matrix has a measure of the impact of a particular hazard on the x-axis and the measure of the likelihood of that occurring on the y-axis. So the likelihood, of course, comes from our ensemble prediction. And we've been working with Rolls-Royce to design, to think about the impact on the x-axis here. So since 2015, the engine manufacturers have been required to produce some certification of the susceptibility of the engines to volcanic ash. And the guidelines coming out from Rolls-Royce are that it's actually not peak concentrations which cause the most damage to your engine, it's actually the duration of exposure. So high concentrations might be relatively benign for your aircraft over a short time, but multiple doses over a long time can lead to problems. So they recommend that if you suspect that you have flown through ash dosages greater than 14.4 grams per meter cubed seconds, then you should, on arrival at your destination, inspect your engine and see if there's anything like contamination of the fuel, contamination of the water, scratching on the cockpit windows, or damage to the turbo compressor blades. So these are all more minor. They're not going to cause your engine to fail mid-flight, but accumulated over time they could. So it's an economic decision about whether to fly based on the fact that you may have to spend more time inspecting on the runway. So the kind of decisions which are available to a flight planner during a volcanic eruption are, first of all, I'm not going to fly, so therefore my company is going to incur some economic penalty associated with that. Or I might decide to fly and maybe put some more fuel on board so that if I'm encountering ash, then I can divert to another airport. That's obviously going to cost some money because the plane is going to be heavier. And also when I get to that airport, I'm going to have to perform extra engine checks, and the longer the planes are on the runway, the more expensive it is for the companies. Or I can just fly the route that I'm planning on flying. So the way a risk matrix works is that you assign a level of risk to each combination of your impact and your likelihood. So for example, a very likely high impact event, you would give that your highest level of risk warning, which here is red, and we also assign that to a high likely moderate impact and a likely high impact. The next level down, your amber warnings are assigned to lower likelihood and lower impact, and then finally the kind of, proceed as normal but check the updates assigned to the lowest level of warning. Now, of course, what values you use for your impact and what values you have up there for your likelihood should really be decided by the individual companies. This comes back to something that came up yesterday about not making the decision for the airlines. It's their company, it's their financial budget. They need to make a decision, and also, obviously, what the model is predicting is not the only thing which is determining whether to fly or not. So it should depend on the individual company and their risk appetite. So it's up to them to design these, but preferably design them before an eruption happens, so that there is some procedure in place. So now, once we have this dosage risk, then the neat thing we can do with this is we can project it into the decision space of the user. So if the user is, should I fly this, user is making a decision, should I fly this route or not, then we can project that information onto the flight route. So what this is doing is it's condensing the multi-thresholds, and it's also condensing the three-dimensional space, because you know about the takeoff and the cruising and the landing, and it's also potentially condensing the time aspect as well, because you can look at the dosage as it's evolving over the time of the flight, the kind of 10 hours or so that it takes you to fly across the Atlantic. So we hope that this is retaining the uncertainty quantification in the data, so it's robust, but it's also allowing fast decisions. So if you're deciding whether to fly, for example, and you're relying solely on the output from the model, then the risk here of flying this route is red, so the action would be consider an alternative route. Now what you'll notice here when we're talking about dosage is that the risk will increase monotonically as we go from JFK to Heathrow and back because of the nature of dosage, with it being an accumulative quantity. However, we are also working with the Civil Aviation Authority, and the Civil Aviation Authority safety risk assessment still relies on peak concentration guidelines. So they wanted us to incorporate peak concentration risk into this product, and that's fairly easy to do. So you can design two risk matrices. Basically, I showed you the one on the right, which is based on the dosage approach, and the one on the left is based on the concentration thresholds. And you can just apply both of them and then display the highest warning, essentially. So the reason I've circled that part in green is because it's a little bit subtle. If I just flick back and forth, you can see that now the risk isn't increasing monotonically, because in this patch we just happen to have some high concentration ash. So we designed this proof of concept tool, and the next thing to try and ascertain was whether this is actually useful for the decision makers who are potentially going to use it. So we designed an online version of the tool, and we sent this to a much wider group of aviation stakeholders, along with some training on how to use the tool. It's very important that they understand how to use it, and also a survey. So what this animation is just showing you is very quickly, it's going to flick through quite quickly, the training that they receive. So for example, what the different charts are designed to do, what the different tabs, this is a layer tab, what the different switches and the tools are doing. So they go through this training so that they understand how to use the tool and how to interpret the information. And when they get to the end of the training, then, I couldn't say it in time with the animation. Now, when they get to the end of the tool, then they click on here, and then there's a survey which they were filling in to tell us whether they thought this was useful for their decision making, and any improvements, and how they thought it might help, or how they thought it was not helpful. So now what I'm going to show you is basically the model agreement maps as they're evolving over time, and also if you hover over the level of agreement, you can see whereabouts in this risk matrix you are, and that's quite important because the same colours are obviously assigned to different combinations here. And you can also then display the risk along the route, like this, and there's some layers as well for things like wind speed, so you can understand how the ash cloud is evolving in the way it's evolving. So there's different layers of information so that different decision makers who require that extra information can access it. To summarise the survey results, all the participants in the survey thought that the fact that we were displaying the information along the flight, so that kind of visualization was really, really helpful. It made their decision making much faster, and they also appreciated that it was better than a deterministic forecast because it did have some quantification of the uncertainty. And there's some quotes on there. So to summarise, what we've tried to do is we have tried to understand how decisions are made by the airlines during volcanic eruptions, and we have tried to design a robust decision support tool which takes into account the uncertainty by producing an ensemble where we perturb a lot of the parameters. We have tried to understand the concern about the fact that uncertainty information can make it more difficult to make a decision because you're presented with a whole folder of information. So we've used the risk matrix approach to condense the information, which is hopefully useful for making fast decisions. And then we've projected that onto the routes. And we hope that this maybe is providing an example of how route-based perspective can be used in other aviation hazards. So, for example, turbulence, SO2 dosage, aircraft icing, to name a few. These are all presented to the pilots and to the airline planners in a big sheet of paper, a big folder, and it's very difficult. If we can condense this information, then it may make the decisions a bit easier. Thank you very much.